Swayamprabha. Digital India. Educated India.
In our previous lecture, we were discussing about some of the important aspects of low Reynolds number hydrodynamics, and we started with analyzing the continuity equation. So, to summarize what we observed during our analysis, let us look into the slides. So, we made an assumption that the flow is 2 dimensional and constant density flow, and the continuity equation revealed a relationship between the velocity scales with the corresponding length scales. So, we made an important comment that the length scale, if the vertical direction is the y direction, then the length scale along y is h, but the length scale along x, it may be the total length of the channel or it may be even less than that, depending on whether there are characteristic changes taking place over shorter distances. Like for example, if the channel surface is patterned with a particular weightability, then it is possible that x reference, the reference length scale along x, is much less than the total axial span of the channel. With this background, let us now move on to the board to discuss about the corresponding implications for the momentum equation. So, let us write. So, let us consider the physical problem in hand. So, there is a channel like this, you have x axis laid in this direction, y axis laid in this direction. So, x momentum equation del u del t plus u del u del x plus v del u del y with a rho is equal to minus del p del x plus mu As obvious, I am not repeating again that we are making an assumption that the flow is incompressible. So, that you know the additional term, source term due to the compressibility effect is not appearing here. Now, let us make an assumption that it is a steady flow. We will discuss in details about some unsteady flows. So, first let us consider that it is a steady flow. So, example, steady flow. So, the steady flow will have del u del t equal to 0, then we consider the orders of magnitude of various other terms. So, this term is not there for steady flow, but let us consider the other two terms. So, rho u reference square by x reference, that is the order of magnitude of this term. What is the order of magnitude of this term? Rho v reference into u reference by y reference. Now, v reference is related to u reference through the continuity equation. So, let us write it once more, the continuity equation. So, our analysis revealed that this is of the order of u reference by x reference. I am not committing whether x reference is equal to the length of the channel or not, because we discussed that it depends on the physical situation on hand, and this is of the order of v reference by y reference. So, v reference is of the order of u reference into y reference by x reference. So, that means this term is also of the order of rho u reference square by x reference, right. So, if this term is important, this term is also equally important until and unless V is identically 0, and this is something which is not very intuitive, because intuition says that V is much less than u if y reference is much less than x reference. Despite that, V del u del y is of comparable order as that of u del u del x, because although V is much less than u if y reference is much less than x reference, still del u del y may be much greater than del u del x. The gradient in the y direction is likely to be much sharper or steeper as compared to the gradient in the x direction. That makes up for the fact that V may be much less than u. So, the product u del u del x and V del u del y, they are coming out to be of comparable order. Let us now look into the viscous term. The pressure gradient term we will consider separately. Let us consider the viscous term. So, the viscous term, what is the order of this term? Mu u reference by x reference square, and this term is of the order of mu u reference by y reference square. If y reference is much less than x reference, again I am telling that this is not always true, but this is true in many cases when there is no pattern of slip or pattern of weightability along the axial direction of the channel, then you can say safely that y reference is much less than x reference. So, if y reference is much less than x reference, then this term will dominate over the other, okay. So, you can see that then this term is going to be the deciding factor as compared to the other term. Look into the similarity between this and the boundary layer theory. In boundary layer theory, you have the boundary layer thickness delta much less than L. So, there the delta is a naturally evolving length scale. Here the y reference may be governed by the confinement height of the channel. The micro channel confinement can decide or can dictate what is y reference, but although scale wise the treatments are very similar, you have to understand very carefully that the boundary layer theory is valid for high Reynolds number, whereas here we are doing a low Reynolds number hydrodynamics. So, physics is completely different, although scale wise you can see that there is some analogy. This has to be remembered very carefully, that this analysis is not what we intend to do for boundary layer theory, although scale wise they are appearing to be similar. So, now let us write the ratio of inertia by viscous. So, let us take an example with y reference equal to h, x reference equal to L, which is much greater than h. Let us say this is an example that we take. So, let us write what is the ratio of inertia force by viscous force. Inertia force by viscous force. So, what is the inertia force? The left hand side is the inertia force. So, inertia force is of the order of rho u reference square by L. Now, we have taken an example with x reference equal to L, and the viscous force mu u reference by h square. I am sorry that this is not visible in the board, I will write it at a separate place. So, write it here. Inertia force by viscous force is of the order of rho u reference square by L by mu u reference by h square. Okay. So, this is what rho u reference h by mu into h by L, right. So, if h is the characteristic length scale of the channel, this is the Reynolds number based on h. So, you can see that the ratio of inertia force by viscous force is the Reynolds number into h by L. So, one very important and interesting observation is that if the Reynolds number is small, h by L we have already committed as small, then the inertia force can be neglected as compared to the viscous force. So, the left hand side of the Navier-Stokes equation becomes irrelevant. So, then that equation is called as Stokes equation. Stokes equation is Navier-Stokes equation with the inertial terms equal to 0, I mean approximately 0, not identically equal to 0, but approximately equal to 0 or neglected, that is called as Stokes equation. So, then when you have the Reynolds number relatively high, you can see that then also it may be possible that inertia force is negligible as compared to viscous force, because the Reynolds number may be relatively high, not too high, but h by L is small. So, the product of Reynolds number and h by L is important. This is the very important take home message, that it is not the Reynolds number that we are bothered just about, but it is the product of Reynolds number and h by L. So, even if the Reynolds number is not too small, but the product of Reynolds number and h by L that is small, then this effect is that the inertia force may be negligible as compared to the viscous forces. So, then what is our equation that we are left with? We are left with the Stokes equation. Let me write that. Of course, it can include other body forces, but here we are discussing mainly pressure driven flow. So, I have not included any other body force. So, you have 0 approximately equal to I have purposefully retained both of the viscous terms, because it might so happen that they are equally strong, but still the left hand side can be omitted if the inertial force is negligible as compared to the viscous force. So, for the example that we have talked, the special form of the Stokes equation boils down to because this term is negligible for that example. What about the y momentum equation? What about the y momentum equation? For the y momentum equation, you can make similar analysis and write okay, similar, just replace u with v. Now the question is, out of these two terms, which term is more dominating? So to do that, let us write what is the order of del square v del y square. What is that? This is of the order of v reference by h square, and order of del square u del y square is of the order of u reference by h square. If v reference is much less than u reference, which is true if x reference, if y reference is much less than x reference, then this term is much less than del square u del y square. This is u. So now apply a logic. You have these two equations. Now in this equation the pressure gradient term is being balanced by the viscous term. In this equation also the pressure gradient term is being balanced by the viscous term, but the viscous term in the second equation is much less than the viscous term in the first equation. Therefore the pressure gradient term in the second equation must be much less than pressure gradient term in the first equation. So this analysis implicates that del p del y is much less than del p del x. If that is so, then you can write del p del x approximately as dp dx. Okay, I am writing it again because this part of the board is not visible. So del p del x is approximately equal to dp dx. So then we are left with this equation where this can be replaced by dp dx approximately. Okay. So in low Reynolds number hydrodynamics we get an equation, if y reference is much less than x reference, we get an equation which remarkably resembles with fully developed flow. That is why we discussed with fully developed flow to begin with. So now the question is, where is the similarity and where is the dissimilarity? So let us write the equation. So we will divide the board into two parts. In one part we will write the low Reynolds number equation, on another side we will write the fully developed flow equation, and that will help us to compare. So we assume that the physical problem on hand is flow through a channel 2 dimensional situation. So, fully developed flow. We had del u del x is equal to 0 and 0 is equal to minus dp dx plus mu d2u dy2, right. Load Reynolds number flow. This is fully developed flow, this is load Reynolds number flow. Load Reynolds number flow does not require del u del x equal to 0, right. So, load Reynolds number still you will have del u del x plus del v del y equal to 0. So, in fully developed flow if there are no holes in the walls, then that will mean V equal to 0 identically, but load Reynolds number flow does not require V is identically equal to 0, right. So, V may be small as compared to u if length scale along y is much small as compared to length scale along x, but if the length scales are comparable u and v may be comparable. On the other hand, when you have no holes on the wall of the channel, then for fully developed flow V is identically equal to 0, no question of any approximation much less or close to this kind of approximation, nothing is required. Not only that, the x momentum equation this is approximately equal to, right. Although while solving problems we will not write always approximately equal to, we will assume that as equal to just in the casual spirit of solving the problem, but fundamentally it is approximately equal to, because the inertial term is negligible as compared to the viscous term, but the inertial term is not identically equal to 0. For fully developed flow the inertial term is identically equal to 0. Not only that, you see that this in place of del p del x we have written dp dx. Here for fully developed flow that is an exact behavior, that is an exact condition. On the other hand, here in place of del p del x we had written dp dx, that is an approximate consideration by comparing the terms in the x momentum with the terms in the y momentum equation. Finally, here you can see that these are partial derivatives, whereas this is ordinary derivative. Why these are partial derivatives? Because now u is a function of both x and y, because u del u del x is not equal to 0, identically not identically equal to 0. So, u is a function of both x and y. So, this is a partial derivative, whereas this is an ordinary derivative. Many times however, see these are small intricate tidbits, but these tidbits are important in the conceptual paradigm, but for somebody who is just interested for solving a problem, maybe there is no great difference between this equation and this equation. So, that is why we have worked out some problems related to fully developed flow that can give you a glimpse of how to solve related problems on low Reynolds number flow, need not be necessarily fully developed. So, we had made this discussion which is sort of like a comparison between low Reynolds number flow and fully developed flow. Let us now summarize these discussions as we go to the slides. yes, this is dpdx, right, this is dpdx, yes. Now let us go to the slides. So I mean because of some version in the version problem in the computer, what you are seeing here as square box is basically of the order of tilde. So that has not come properly in the version of the PowerPoint used in this computer. So that but assume that well, tilde has come properly, what has not come is much less. So much less has not come. So